Swayam Prabha. Digital India. Educated India.
Hello and welcome back once again to this lecture series on aluminum based alloys and metal matrix composites. So in the previous class we have learned about all the strengthening mechanisms of metal matrix composites. And with regard to this we have talked about the shear lag model or the shear lag theory, which talks about the transfer of the load to the stronger reinforcement via the interface. And then we talked about the dislocation mechanisms such as O1 strengthening, work hardening, grain refinement strengthening, and strengthening due to mismatch in the thermal expansion coefficient. Right, so all these mechanisms will ensure that the strength of a composite is higher compared to the unreinforced matrix. Okay, so now that we have learned about the strengthening mechanisms, it is time for us to have a look at the fracture behavior of MMCs and see how the fracture of the composite differs from the matrix material and what are the different aspects of fracture. So this will be the topic of discussion for this particular class: fracture of metal matrix composites. So we are going to start with again the fiber reinforced composites. So when you talk about the fracture behavior of a fiber reinforced composite which is loaded in a particular direction, let's say in the direction parallel to the fibers, then you need to also consider how the matrix behaves as it is loaded in the presence of the fibers. Okay. So you need to consider the matrix properties as well, particularly the ductility. Because the material flow in the matrix will be decided by the ductility. I mean, how far it can go through the plastic deformation and accommodate it. That is what the ductility talks about, right? So for a ductile matrix, the ultimate strength of the composite material is relatively insensitive to the matrix behavior. That is the first point to note. And apart from this matrix behavior, you also have to look at another important aspect, that is the fiber matrix bonding. Because as we have seen before, the load will be transferred through this fiber matrix interface, and therefore the interface bonding will also play an important role in the fracture behavior of composites. So we will make distinction between two cases with regard to the ductility of the matrix. One is when the matrix is quite ductile, and another when it is a stronger matrix and the ductility is relatively lower. Okay, so ductile matrix, for example, if you talk about pure aluminum matrices, then you can say that the fibers can fracture before the global yield of the matrix. So before the matrix starts to yield, you can expect the fibers to fracture when the composite is loaded, when the matrix is ductile. So now once the fibers are broken, then the crack will propagate along the composite, and this crack propagation would depend on what kind of interface bonding is there between the fiber and the matrix. Okay. So let us consider a fiber reinforced composite like this. So what we are saying is the fibers will be broken. The fiber will fracture first, and how this crack will propagate, that depends on the bonding at the interface. Okay, so this is the interface that you have over here, right? So this interface, how it behaves, depending on that, the propagation of the crack would vary. Okay, so again here also we can make distinction between two cases. One when the interface bonding is strong, and the other when the interface is weak. Okay, so here once the fibers begin to fail, local matrix will yield at the broken fiber ends, and this yielding of the matrix at the broken ends of the fibers will relax the stresses and will prevent the crack from propagating to the adjacent fibers. Okay, so what we are saying is once the matrix yielding starts, it will basically lead to stress relaxation, and this will have a blunting effect on the crack tip, right? So here at the end of the fibers, at the broken end, it will basically relax the stress and blunt the crack. And this will prevent the crack to propagate to the adjacent fibers. Okay, so when you have a scenario like this, matrix yielding in a ductile matrix material, then it can have a relaxation effect on the crack, and the crack propagation will be prevented, right? So this is one scenario where the matrix is soft and ductile, right? So now let us move to another case where the ductility is comparatively lower. So for that kind of material, for brittle matrices, the failure of a single fiber may propagate through the entire composite. So it may lead to catastrophic failure, because once the fracture starts in a particular fiber, it will quickly propagate to the adjacent one, and the crack will quickly propagate across the entire composite material. So the catastrophic failure or the catastrophic fracture of the composite can be prevented only when the fiber matrix interface is weak. Okay. So this scenario, if you see in terms of, again, looking at the fibers, okay, so once the fracture of a fiber starts, it will propagate to the next one, right? And as I said, the catastrophic propagation of the crack can be only prevented if some relaxation is developed at the crack tip, right? So only when the stresses can be relaxed, this kind of catastrophic propagation of the crack can be prevented. And in this case, when the matrix is brittle, that relaxation can only be developed through the interface if it is weak, if the bonding at the interface is weak. So this will relax the fibers and prevent the catastrophic crack growth. And this is also one of the reasons of the anisotropy that you see in fiber reinforced composites. Because how this interface will behave from fiber to fiber, that might change, and it may also differ when you change the loading direction, right? So that is how this interface behavior can lead to anisotropy in fiber reinforced composites. So when the interface relaxes due to the weak bonding, it can be represented in this manner. So basically what we are saying is, when the fiber is fractured, it can be relaxed if there is a debonding at the interface. Which will lead to crack deflection and prevent catastrophic fracture. So now let us consider the fracture of a single fiber and how that propagates to the adjacent fibers, leading to the complete fracture of the composite. Okay. So the load carried by a particular fiber has to be distributed to the adjacent fibers before the fiber fractures. So load redistribution is needed. Before the fiber fractures. And therefore the load has to be transferred to the adjacent fibers, and then those fibers will carry the load. And as you continue the deformation of the composite, these fibers will now start to break, the fibers which now carry the load. Okay. So as you continue the deformation or continue to increase the load on the composite material, the fibers will break one by one as the load is redistributed and the load is transferred to the adjacent fibers. Okay. So this sequential fracture of the fibers will depend on the degree of coupling between the fibers and the matrix. So this again boils down to the bonding between the fibers and the matrix. So it is not difficult to understand that when there is no coupling, then the composite under load will behave like a bundle of fibers. Right? Because the matrix has no role to play over here since there is no coupling between the fibers and the matrix, right? On the other hand, when there is a strong coupling, then the deformation will take place in a manner what we discussed before, right? Depending on different parameters of the matrix material and also the interface bonding, it will deform in a particular manner as we discussed. Now, let us consider the growth of large cracks during tensile loading in a direction parallel to the fibers. Okay, so let's say this is a fiber reinforced composite which is loaded in tension in a direction parallel to the fibers, right? And now we need to understand the growth of large cracks as to how it happens in this case. So in this case, for the crack to propagate, failure must occur in both the fibers as well as the matrix. So you have a crack in the fibers and you also have a matrix crack. Okay. The matrix crack propagates behind the fiber crack front. That means the matrix crack will follow this fiber crack, right? Yeah, so if this is the crack in the matrix and this is the crack in the fiber, so this is how the matrix crack will be with respect to the crack in the fiber. Okay, so the propagation occurs in that manner. Okay, the matrix crack propagates behind the fiber crack front. So here you can see the crack front is planar. And this occurs when the interfacial bonding is strong. On the other hand, if the interface is weak, then debonding at the interface will lead to crack blunting, as we have seen before. So due to the weak interface, there is debonding at the interface, which will lead to relaxation and blunting of the crack. Something like that, right? So there is a debonding at the interface, which leads to crack relaxation, right? Or crack blunting. And in this case, you can see that the matrix crack and the crack in the fiber are not really in the same plane. So therefore, here the fracture is non-planar, unlike the previous case where it was a planar fracture or planar crack front, right? But in this case, the matrix crack and the fiber crack are not necessarily in the same plane, and therefore it is a non-planar type of fracture. So to quickly summarize this fracture behavior of fiber reinforced composites, we can say that when you talk about the entire fracture of the composite material, you need to take into account the matrix behavior and the fiber matrix interface. Okay, so depending on that, the crack will behave or propagate differently. And matrix properties such as the ductility of the matrix will have a role to play on the propagation of the crack. When it is a ductile matrix, the yielding of the matrix material at the broken fiber ends leads to stress relaxation, and that will prevent the propagation of the crack. On the other hand, when it is a brittle matrix, the crack can propagate from one fiber to the adjacent fiber, and the catastrophic failure can only be prevented if there is a weak interface which leads to some kind of deflection of the crack due to the debonding at the interface. Okay, and then we talked about the fracture of single fibers as to how the fibers fail one by one when the composite is loaded, and this sequential fracture of fibers depends on the coupling between the fiber and the matrix. If there is no coupling, the entire composite will behave like a bundle of fibers, and on the other hand, when there is a strong coupling, the fracture behavior would depend on the interface bonding. Okay, and then we talked about growth of a large crack under a tensile load in the fiber direction. So here again, depending on the interface bonding, the fracture can be planar or non-planar. When the bonding is strong, it will be planar. The matrix crack will follow the fiber crack, and these two cracks will be in the same plane. On the other hand, if it is a weak interface, debonding leads to crack blunting effects, and here the fracture of the fiber and the matrix are not necessarily in the same plane, so this will be a non-planar type of fracture. And with that, we come to the end of this lecture. Thank you for watching.